Will Stevens, and I will be talking about our third lab where we're going to be looking at objects orbiting a black hole. So first, our purpose of this lab is to look at objects, just as I said, going around a black hole in gravitational motion with regard to Newton's second law of the momentum principle. And we're going to use the perspective of perpendicular and parallel motion to better understand this phenomenon. And our main results is that we're going to find the mass of a black hole given an orbiting star's mass and trajectory, and then later find the trajectory of a ship needed to leave an orbiting planet of that black hole. So now let's look at the momentum principle. We can break force equals mass times acceleration into mass times the change in velocity, which equals the change in momentum over time. And then in our scenario, if we want to look at parallel and perpendicular forces / components, we can look at it like this. We have circular motion, so our parallel direction is going to be tangent in the direction of the motion of the circle, whereas perpendicular is going to be inwards toward the center of the circle. So as we are looking at it in parallel and perpendicular components, we can say that the net force is equal to those two combined. And then we can find the parallel force using the change in the magnitude of momentum over to the change in time times the unit vector to get the parallel component of the force. And then we can subtract that from our net force to find the perpendicular force. You can do it a couple of different ways, but this is the way I did it. And then we have the gravitational force in this scenario, which is the normal gravitational force formula, and then we can say that the total net force is equal to that gravitational force. So you can plug in the net force into this equation and then rearrange for that mass of the black hole, which is exactly what we're going to do. So this is the trajectory that was given for me, and then from that, as I'm about to explain, I found a mass of 1.14 times 10 to the 34 kilograms. And this is, of course, with our system being our planet and the surroundings being the black hole and the rest of the universe. So let's go through the code. So just as I talked about before, we're going to find that change in momentum and velocity, and then we're going to apply that into the momentum formula to find our net force. And then we're going to find that parallel force component and then use that to find our perpendicular force component. Now, we're going to solve for the mass of the black holes with that gravitational force formula, as I talked about earlier. And then we're going to indicate the direction of each of our forces that we calculated earlier, just with the corresponding unit vector. And then, of course, because we are finding the mass of this black hole, each iteration that we are increasing the time, that's the mass at a certain time. So we need to take the average of that across that time period, which is what that line down here is doing. So then we can also, for our scenario 2, now we're going to be looking at the ship leaving a orbiting planet. And we're first going to find all the forces in this case. So we're first finding the force on the planet due to the black hole, the force on the planet due to the ship, the force on the ship due to the black hole, and the force on the ship due to the planet. Then we can use that to find the net force on the ship, and then update the position and the velocity of both the ship and planet, so that now we can plot all of this in our model. And then I also have down here an if statement that's going to allow us to find that minimum distance between the ship and the black hole over that time period. So this is what it looks like. You can see that the ship very clearly left the system. This is the velocity I used, and then the minimum distance using the if statement that I got was 2.37 times 10 to the 9th meters. And in this case, our ship is the system, and the surroundings is the planet and the black hole. So what are some possible sources of error? Because this is a computer simulation, there's not really any computer error or anything like that. But we could have made the time period longer because it was reading the mass every iteration. We could have just increased that, which would have given us more readings and therefore a better average. We could have also decreased the change in time between those iterations because we're calculating position and velocity update using that net force that we calculate each iteration. And the shorter that delta t is, the more accurate that is as well. So, what is the difference between net force and rate of change of momentum and their components? Mathematically, there is no difference. However, physically, the rate of change of momentum is measurable while net force is not. And then, what if we want to not leave the system but just start an orbit around that black hole? Well, this is a velocity I found that works and allows the ship to, as you are about to see now, to complete that orbit and leave that planet as well. And that is all. Thank you.